Another extra TMUA paper 2 from Jacqueline Tyler. I thought this one was also slightly harder than the other paper 2 that we did a couple of videos ago. But anyway, let's go into it. So very quick one here. We're just going to have a b squared minus 4ac equals 0 check here. So it's going to be this thing squared minus 4 times this times this. This is technically got minus in front, but it doesn't matter because you're going to square it anyway, so completely irrelevant. I did this in a fancy way. I just used a difference of two squares here rather than solve this properly. So it's going to be this one minus this one into this one plus this one. Or I should say the root of this, right? It's 2k all squared is what this really is. So we can use 2k's here. Anyway, simplify that down. And yeah, this has roots of either k is a third or k is minus 1, it looks like that. Except there's also a super secret solution, which is when k is 0. When k is 0, you get the equation just x equals 0, which has one solution, right? X equals 0. So therefore, there are actually 3 values okay to do this rather than 2. Of course, you could have put a non-zero constant k would have fixed this question, but anyway, excellent. Question number 2. Okay, well, I don't think we're supposed to know sine 2x equals 2 sine x cos x in TMUA, so that's fine. We'll just sketch this because it's a how many solutions question, so that's just a sketch question, isn't it? Sine 2x just does sine, but twice between 0 and 2 pi, except I actually only care up to pi anyway, so we can just cut the graph here. Cos x does this, right, all the way along. Now, that's a terrible drawing of cos x, but it doesn't matter because all I'm doing is counting 1, 2, 3 solutions, and that is that done. Now, we can cross multiply this because 2 is always positive and x squared plus 1 is always positive. So we can cross multiply without worrying about this sign being messed up. So that's what we're just going to do. And then we can rearrange and then we can factorize. And this is always true, right? Something squared is always bigger root of 0. So this is just true for all real values of x. Excellent. So here, apparently I am supposed to know that sine 2x equals 2 sine x cos x because that goes to this. That's fine. Now here they've divided by cos x, which they're not allowed to do. I mean, they are allowed to do it as long as they write that cos x could be 0 at this point. Rather than trying to find solutions from here only. So the first mistake is on line 2, I guess. Classic mistake. F of 1 equals 1, which means f of 2 equals 1, which equals 1, and f of 3 equals f of 1 plus 1. F of 1 is 1, so that makes 2. And then f of 4 is f of 2, which we already know to be 1. F of 5, well, 5 is made by using a 2 here, so f of 5 is f of 2 plus 1. F of 2 is 1, so that's just 1 plus 1, which is 2 again. And you just keep going. F of 6 is the same as f of 3 based on this rule. F of 3 is 2, so that's just 2 as well. F of 7 is f of 3 plus 1, and so on. And then we get to 8, and then we get to 9, which is 2. Just follow the pattern. Question 6 then. P is a polynomial. Condition P is that it has at least one real root, and condition Q is that it's an odd polynomial, odd degreed polynomial. P is necessary, I think, for Q, because to check necessity, of course, we're trying to think of a time when Q happens but P doesn't, and we can't do that. We can't have an odd-integer polynomial, an odd-degreed polynomial that doesn't have at least one real root. So P is definitely necessary, but it's not sufficient because at least one real root, where you could have 2 of them, and it could just be a quadratic, which is an even polynomial degree. So it'll be necessary but not sufficient will be our answer. For number 7. Exactly one of these things is true. I decided to go with counterexamples on this. So, for example, I just chose A to be 5 here, and then maybe you just choose B to be minus 10 to make this one not true, but this one true. And then, okay, well, here that's also not true because B squares to 100, so that's great. But here, the modulus of A is less than the modulus of B. And there's no way we're going to be able to do this, I don't think. I think these last two in particular, like the only way you can make this swap over like this is if you use B as a bigger negative, but then you're not really allowed to do that here anyway. So because then this one becomes true. So, okay, we have to be a bit clever with our counterexamples. If we pretend that this isn't the true one, and we maybe say that B is maybe, so you start with numbers a bit like this maybe, then you'll see that it still breaks down for the same reason as the previous one did, right? This one's not true, but then this one is again. You have to be a bit intelligent, but eventually you'll find a counterexample like this. And I'm just using these inequalities, the strictness of them, to my advantage here. Obviously, this isn't true based on this one here. This isn't either because A isn't less than B, it's the same as it. This isn't true either because, again, it's strict sign here. But this one is true because the modulus is less than or equal to. So I think that's the only one that can be true based on this example here that allows me to do it. Question number 8 then. So we have, there exists a number c in between a and b, so p of c is 0. Again, a necessary and sufficient thing. So let's start with necessity maybe. So we're trying to find a time when this thing happens, star happens, but the condition doesn't, I guess. That would check for necessity. And sufficiency, we're thinking of a time where the thing happens, but the star doesn't. So okay, well, if p of a times p of b is less than 0, that means that one of their values is underneath the axis and one of them is over. It doesn't matter which one. But if that's true, and the thing is a polynomial, which means it's a continuous function, it must, somewhere in here, it must pass the axis. It must cross the axis. So I think that the condition is sufficient. Is it necessary? I don't think so, because you could be below the axis both times, and you could just go through it like this, and you still have a root. You'd have at least one. I mean, you could have one if you just touched it, or you could have more than one. It doesn't really matter to the condition. It just says there exists a number, so it's not being specific about whether there's one or not. So therefore, I think it's sufficient, but not necessary. Sufficient because if you have it, then it's going to cause star to happen, but it's not necessary because star can happen anyway. Question number 9. So we've got this function here, but the calculator only works in degrees, which is hilarious. What can the student type to correctly evaluate it? So the first thing to notice is that, of course, this second x on the bottom, lost my mouse there for a second, this second x, now that's not going to be any changing at all. The only thing that's going to be changing is the input into the tan, right? This x isn't going to be changing. So when we evaluate f of 5, we are going to be dividing by 5 at some point. So it's definitely not b, because we're timesing by 5. These have changed this x, but we don't need to change that x. That's just an x. It's not the trig of an x. It's just an x. So that goes away, and this is also times by 5. So these times by a fifth, those are reasonable. Now, which one of these two things is it? Well, 2 pi radians is 360 degrees. So therefore, divide by 2 pi, we get 1 radian is that, and then maybe times by 5. Or cancel this down a little bit, and then times by 5, and we end up with that, which is this one here. Would be one way of figuring it out. Question 10, we have a sequence here. So the next term is just the previous one divided by the one before that. So u3 is going to be this divided by this, which is a half, and then u4 is going to be a half divided by 3, which is a sixth, and then u5 is a sixth divided by a half. Divided by a half is times by 2, so that's a third, and then the next one is going to be a third divided by a sixth, which is the same as times by 6, that's going to be 2. And the next one is 2 divided by a third, which is 6, which is interesting because that's the first one we ever had. The next one is 6 divided by 2, which is 3, which is fantastic because that's the next one. And of course, if you're going all the way to 2023, I'm not going to write these all out to 2023. I'm just going to look for a repeating pattern. And I think I've now found it. Right, it goes 6, 3, a half, a sixth, a third, 2, and then 6, 3, a half, a sixth, a third, 2, and so on. So therefore, the first term is 6, the seventh term is 6, so the 13th, and so on. So this is a sequence of just 6n minus 5, I believe. So what I'll do is I'll just check whether 2023 is in that sequence. Now, if it is, then great. That means the 2023 term is 6. If it's not, if it's like remainder 2, when you try and solve this, that's fine. You just count 2 from the 6. So if it was remainder 2, I think the answer would be a half, right? That's 2 beyond it. Now, when you solve this, it ends up to be no remainder. So therefore, U2023 is one of the 6s, and that's the answer. Question 11, the fact that 5 times 6 is a counterexample for which the product of any two odd integers, those aren't odd, so that's not it. The product of two integers is a multiple of 4, that's not a multiple of 4, so that's not it either. If the product of two integers is not a multiple of 4, well, we're getting somewhere, then the integers are not consecutive, these are consecutive, so it's a counterexample. Excellent. Really not much more to say about that. Okay, this, I'm going to rearrange it, I guess, and then I'm going to sketch it. 3, 4 is clearly down here somewhere, because this is like 12.5, and this is some other big number. 3, 4 is clearly just in here somewhere. So, okay, I'm just going to reflect that in the line. So what I'll do is I'll just try and find the line that's perpendicular to the red line, the original line, and goes through 3, 4. Now, if you do that, of course, perpendicular means gradient 4/3. And then when you put in 3 and 4, you can imagine a plus c here. But when you put in 3, 4, the 3's cancel, 4 equals 4 plus c, and just c is 0. So it goes through the origin, which is great. And now all I have to do is find the intersection between this and the red line, this and this, I guess. I times everything by 12, I think, here, just because I couldn't be bothered to do the maths properly. And this point here is going to be 6, and then, of course, the other point is 2 times 4 is 8. And then, of course, the point in the reflection is just going to be this, follow the pattern, 3 to 6 to 9, 4 to 8 to 12, and it'll be 9, 12, I think will be our answer. Good. 13. Consider 4 statements. One of them is true. Now, if B was true, the statement is true if and only if this x squared less than 1, then that means that A is automatically true. Because if it's true for both if and only if, then it's true for if. So if B was the true statement, then A is also true, which means B can't be the true statement. And likewise, the exact same logic on D. This is just this statement A is just contained within statement B. So if statement B is true, then so is statement A. Now, decide between A and C. Basically, what's happening here, I've crossed out C already, but that's a bit of a spoiler. To decide what's happening here, basically what happens is, let's pretend we're being asked the question, when does X and Y have one intersection? Okay, well, you do some maths, and you do some maths, and you do some maths, and you end up, let's pretend, you end up with the condition x squared less than 2. So you've done some maths, and you've learnt that your condition for when these things have an intersection is when x squared is less than 2. But that means that if these were your choices of answer, if these 4 things were your choices of answer, then A is also a true thing you could write down, right? Like you could circle A. If the statement is true for x squared less than 2, then the statement is true for x squared less than 1. Right? Because again, it's just within this answer here. Like it's not the whole answer. You've missed a bit out, but that's fine. If it's true for less than 2, then it's true for less than 1. So therefore, we have to cross out this, and the answer will be true for A here. That's the only one that doesn't imply any of the others to also be true. Question 14. What's the minimum value of this? So I think my idea here is, now it's only between 2 and 0 here, notice. So let's evaluate it at 0 and 2. That doesn't take too much work, but it is a bit annoying, but it's fine. So at 0 it's worth 3, and then at 2 it's worth 7, fine. Now it could just increase here, in which case the minimum value would be at 3, or it could come down and have some minimum point down here, or whatever, I'm not really sure. So what we'll do is we'll differentiate to find whether it has any minimum points. So differentiate, set to 0, divide by 6, solve it, get x is 2 and 1. Now, that means that this is a turning point, which doesn't really matter to me, but x equals 1 is. Put x equals 1 in here, and you get f of 1 is 8, which is way up here somewhere. So the graph must kind of come up and then down and up again, which makes sense as a cubic, so it comes like this and this and this. But that means the minimum value between 0 and 2 is this value of 3 at 0, the thing that we found right at the very start. Question 15 kind of completely scuffed this question, I think. But what I did was I sketched this graph, so it's just a circle moved 1 to the right. I think, radius 1, of course. And then I said, okay, well, here's the original kind of x squared plus y squared equals 1 circle. And now think about the largest x plus y can be. Now, clearly, we're looking in this quadrant because we want x and y to both be positive. Otherwise, if 1 is negative, then it will just start cancelling, and we don't want that. So, okay, well, the obvious point to think about is just this one here of 1 over root 2, 1 over root 2. Because, of course, when you square those and add them together, you get 1. So that's on this red circle here. Now, when we add those together, we get 1 over root 2 plus 1 over 2 is 2 over root 2, which is just root 2. And now all this graph is a translation 1 to the right. So therefore, the x coordinate has increased by 1 to become this. And now if I add those together, I'll just get 1 plus what we just had, which is one of the answers D. And these answers are in side order. So D is the answer as long as I can think of some reasonable way of discounting the answer of 4. Right? Then D will just be the largest. So okay, what I did was I expanded this out, and then I cancelled the 1s, and then I kind of refactorized this into this, and then I added that to both sides. Now, x is definitely, if x is within or on this circle, x is definitely less than 2. The biggest x can be is 2 just here, and the biggest y can be is 1. Now, there can't be those two values at the same time, but that doesn't matter. The biggest x can be is 2, and the biggest y can be is 1. So therefore, I think 2x plus 2xy is definitely less than 2 times 2 plus 2 times 2 times 1, which is 8. And then if we square roots, we'll get that x plus y is definitely less than 2 root 2, which is less than 4, I believe. I think it's like 2.8 or something like that. So I think D must therefore be the largest that we can possibly get here, just based on the answers. Given x equals minus b as a root of this, so that means by factor theorem, if we do f of minus b, we'll get 0. So let's put minus b in here. These ones turn into negatives, and that one stays the same, and we get this. Now, b equals 0, I guess, can go away here. As long as we make a note of it, I guess. Sure. And now this is just a quadratic in B. So I guess we can just use the quadratic formula and get this. Now, this doesn't really work if A is 0. Let's just notice maybe that if A is 0, we get f of x equals b. And then, okay, well, then it's apparently got a root at minus b. So that means f of minus b must be 0, but that will just make b 0. And I guess that's fine. You have a root, and that's all good. That's just a trivial graph of f of x equals 0, I guess. That's fine. No problems with that. And okay, let's crack on then. So now we need this thing to be positive, I guess, because otherwise b isn't going to equal a real thing. I guess this is implying that it should be a real number. I guess it's implied here as well. So okay, let's sort this out. We can cancel that down. This is an upside down quadratic, and the roots are at 0 and 4/3. So therefore, we want to be in between those two roots to be greater or equal to 0, since it's upside down. And I think C will be our answer to that. Question 17 then. So what I did was I rearranged these all into exponential form, and then I just tried to get rid of the C's, I think. So what I did was I just rearranged this one for C, and then just threw it in here. And then I think what we can do here, or in fact, yeah, I tried getting A out of this, but found it fiddly. So I decided to do B instead. So A squared is B to the 4, obviously, and put that in here. And then just make an equation for B. If you do some maths, eventually it turns out to be this. So now how many solutions for B does this have? Well, if we sketch the graph, maybe, we can probably figure it out. Because, okay, that's differentiates. This is just me differentiating it and turning it to 0 to try and find stationary points. So obviously it's got stationary points at b equals 0 and b equals 3, I guess. I don't really care where that stationary point is. I can tell it's negative because 3 to the 4 is 81. 3 to the 3 is 27, but times by that by 4, and that's bigger than 81, and then add the 1 doesn't make a difference. So the graph looks something like this. It's a quarter graph, so it starts up here and ends up here. One of its stationary points is repeated, which kind of implies maybe an inflection point. And so it does this and then comes down. At 3, it's got a negative y position, as we figured out, and then goes back up again. So this has 2 solutions for b. Importantly, 2 positive solutions for b, which means when I square them, I'll get 2 solutions for a. Maybe it's actually not important that b is positive. Who knows? Anyway, 2 solutions for a, I think it will be the answer to that. Number 18 then. So this is an interesting question. Sine to the power 64. Now, sine is always between 1 and -1. When you raise that to the power 64, 2 things happen. 1, it's always positive. So this area doesn't just cancel with itself because this graph is always above the x-axis. But 2, anything less than 1, or modulus less than 1, raised to a big power, just becomes closer and closer to 0. So I think without really any effort, I think this graph here, this integral, is basically 0. Like it's so close to 0 as if not to really put it in Wolfram Alpha, test my theory. I think it's basically just 0. Anyway, this one here is also interesting because cos to the 6, again, I don't even need the power 6 here. The cos graph is always 1 or less. So when I take away 1, imagine shifting the graph down by 1. It will just always be negative. The entire graph will be in the negative area. So therefore, when I do an integral, the integral is going to be negative because the entirety of the graph is below the axis. So this is some negative number, just thinking about the graph. This one here, again, interesting. Between 0 and 1, sine to the power 6, now that's a positive thing. But x squared minus 2, again, between 0 and 1, that's a negative thing. Right? You square something between 0 and 1, gets you between 0 and 1. Then you take away 2, that's a negative thing. And then when you times it by a positive, you're still negative. So this entire graph for this range is also below the x-axis. So it's also a negative number. So we can cross those 2 out because although this is basically 0, it is a positive basically 0 number. So this is therefore the biggest of the 3 so far. But then you look at this one and realize that all your effort is basically pointless because when you take the sine graph and add 3 to it, well, that just puts a relatively enormous amount of area underneath the graph and the x-axis. When you raise that to the power 6, it becomes an even more enormous amount of area. And maybe you'd be distracted and think, well, between 0 and 4 pi, all the areas will cancel. No, they won't, because the graph is all massively above the x-axis. So nothing's going to cancel here. This is the answer by quite a long way. So yeah, quite a nice question though, really nice. Which of the following statements is true? There exists a real number y such that for all x, y is bigger than x. So basically this is saying, can you just pick a y such that it's bigger than all real x? Or no, there's no biggest number that you can possibly pick in the world. So we can't do that. Again, can you pick a number x such that for all y, this is always true? Takes a little bit of thinking, but of course, what's basically the only way in which multiplying is always going to be less than adding? Well, if you multiply and add by 1. And you'll end up with something that's always true for all real values of y. So that one is true. So 2 is true. And this one here looks much more complicated, but we'll do a similar thing to what we did before, which is use the quadratic formula on some unknowns. So this is a quadratic in y, just use the formula. If x is 0, well, if x is 0, you can just go back to this and you can say you need minus y to equal 1. So therefore, there does exist a y that can do that. So that's fine. And then we just need this thing to be positive to get real y's. So we just need that to be positive. Very similar to what we did before, actually. And we get this, but then we factorize that, and we turn out it is always positive or equal to 0. So therefore, that's fine as well. So 2 and 3 are the true statements. Question 20 then, to finish up. Now, if you've watched my video on if and only if, you'll have a banging time with this question. What we want to do is we want to write all of these as if-then statements. So, for example, this first one, it actually says if and only if. So that means it's both if this, then that, and at the same time, if this, then that. You have to have both of them be true at the same time for if and only if. Only if means if the first one, then the second one. If means if this, then that. So if second one, then first. If, so if this one, then that again. Only if means if the first, then the second. And only if again, if the first, then the second. Now let's look through these in turn, because statement A needs this thing to be true and this thing to be true. But if we look down the line, D is the same as this part of A. So if A is true, this thing and this thing are true, then this thing is true. And therefore we have two statements true at the same time. Where, again, it's one of these questions where we're looking for one of them to be true. So that one can't be true because it means D is also true automatically. B and C, it was very helpful that B and C were written next to each other because it makes it easier to spot that B is of the form if P, then Q, and C is if opposite of Q, then opposite of P. So if not Q, then not P. Now, these are called contrapositives, and contrapositives, if one statement is true, then its contrapositive is logically also true. So therefore, these two things imply each other, and neither of them can be the correct statement because they both make the other one true. Now, D, I think, is also a contrapositive, is it? Yes. If P, then Q. If not Q, then not P. I think D and E. So therefore, D and E are also taken out for the same reason, and E is the true one. It's the only one that is left, and so it's the true statement. A fantastic paper. Really enjoyed it. Incredible stuff. Genuinely, really, really good paper. Had a fun time. Thanks for watching.